Okay, excuse the quality of this video. I'm just trying to get this done as soon as possible so that you guys can have this to review. So we're working on practice or notes sheet number 3, and I wanted to let you know what the answers to all the questions are and explain them as I go. This is a graph that can be folded in half or can be folded along a line so that the two halves match. That's called reflection symmetry. When you reflect across, flip from side to side, or up and down, then it's the same. Rotation symmetry is when you can rotate 180 degrees. So if you turn this entire graph over, flip it over, then this part will go down here, and this part will go down here, and it'll be right on top of itself. So this has rotation symmetry about the origin, and this has reflection symmetry about the y-axis for this one, and the x-axis for this one. The common lines of symmetry are the x-axis and the y-axis. And the common point of symmetry is the origin. This is important because we're going to be looking at those particular types of symmetry when we look at different functions. These are the graphical and algebraic tests. So when you have a point xy on a graph, and you want to test whether or not its opposing point is on the graph for x-axis symmetry. So that means like this one, where you take a point x comma y, and you're going to look at it, it's going to translate downwards to its reflected point. It has the same x-coordinate, but its y-coordinate is going to shift to negative y. So it's x comma negative y. And if it was negative to begin with, it would become positive. This goes both ways. Negative simply means negate whatever it was before. So x comma negative y. So that's what we're going to put right here. So in other words, what we're doing is we are replacing y with negative y. Similarly, if we are reflecting over the y-axis, then the y points, the y-coordinate is not going to change, but the x-axis is going to change, the x-coordinate. So it's negative x comma y. In other words, you're flipping across here. You are moving from one side to the other of this graph. X's will become the negative of whatever they were previously. And so we're replacing, in other words, x with negative x. And what's interesting here is that for the different types of symmetry, origin symmetry is actually a combination of both. So if you do a flip in the x and in the y, a reflection over x and a reflection over y, that means negating both terms, so negative x and negative y, then it's actually the same thing as doing a 360-degree rotation. You can convince yourself of that if I flip this graph over, so up and down, so over the x-axis, and then across, so over the y-axis, then it's actually going to be the same as if I just take this whole thing and rotate it 180 degrees, which is pretty interesting. So with origin symmetry, you replace x with negative x, and you also replace y with negative y. These are all the algebraic tests for different types of symmetry. So you can do this algebraically or graphically. I'm going to use the graphs here and show you some of the answers. This one has y-axis symmetry because it's symmetrical across the y-axis. Because if you flip it side to side across the y-axis, it's the same on both sides. However, it's not the same up and down. So it's not symmetrical across the x-axis, because if we flipped it over, it would look something like this, where it goes downwards instead of upwards. And if it doesn't have both x and y-axis, then it can't have origin symmetry, because origin is actually just a combination, as we just learned, of those two. All right, that's the other one here. If you take xy equals 6, so we'll look at this one. It says x-axis, y-axis, origin are none. In this case, it is not symmetrical if I do I'll flip over the x or y axis, because if I flip over the y axis, then it's going to be mirror imaged like this. And it's not going to be exactly the same. It's going to be this reversed graph that I've drawn in pencil. So it's not y-axis symmetrical. It's not x-axis symmetrical because of the same reason. It's going to flip over this line. It's going to flip downwards here to the opposite end and upwards here to the opposite end. So it's not going to be symmetrical. But if I do both of them, that is, I do a 180-degree flip where everything goes to its opposite end, then actually it is symmetrical. So this has origin symmetry, and that's the only one. Going back to this one, if it's got y-axis but not x-axis, it doesn't have origin, but it can have origin without having both of these. So it could be origin but not x-axis or y-axis. But it is symmetrical under a combination of the two. Okay, flipping over to the other side, do a couple more examples, and I'll breeze through these ones real quick. So this one is none. While it might look symmetrical, it actually isn't because it's symmetrical, but over, say, this line, for example, right? Oh, apologies, it's not none. It's symmetrical over the y-axis. It's not symmetrical over the y-axis, but it is symmetrical over the x-axis. It is symmetrical over the x-axis. So if you flip it over this, where you bring top to bottom and bottom to top, then it is actually the same. So I'll erase this. Apologies, this is not none. This is actually x-axis symmetrical, but it's not y-axis, so it can't be origin symmetric. And if you flip it around the origin, erasing some of this, if you flip it around the origin, rotating it 180 degrees around 0, 0, it's going to end up roughly over here. And that will not, where the bottom becomes the top and the top becomes the bottom, these two flip onto each other. So this has x-axis symmetry only. For number 4, this actually has all types of symmetry. This has all types of symmetry because if I reflect over the x-axis, top to bottom, it's the same on top and bottom. It's also the same side to side everywhere you look. So it's got x-axis, it's got y-axis, and if it's got both of those, then it's got to have origin as well. And that's the case because if I rotate it 180 degrees, it ends up back where it began. You can basically see that if I just take the paper, turn it over, it is exactly the same picture as it was before when I turn it 180 degrees. Notice that it has to be around the origin though, because the origin here, 0, 0, is the center. So the answer is all 3 for this one. Let's look now at number 5. Number 5, the answer is none here. Ask me a question independently if you would like to see why, but basics is that it's symmetrical, but not around any of these particular things. You can flip it over any of those things, it's not going to work. And this one is, it can't be x-axis symmetrical because it's not the same top to bottom. It's not like this, where it's the same top to bottom. It is y-axis symmetrical, however, because it's the same on both sides of the y-axis. So if I look at the y-axis, right there, on both sides of that, it is exactly the same. So y-axis symmetry for sure. And if it doesn't have both, it can't have origin, but let's check if I do this. If it has one but not the other, I should say. If it has one x-axis or y-axis but not the other. If it has both, it definitely has origin. But if it only has one or the other, it's not going to have origin. And you can try rotating 180 degrees. And of course, flipping it over makes it look completely different, where it opens upwards instead of opening downwards. All right, there are all our examples. Let's look at even and odd functions now. Zooming us out a little bit. Even and odd functions. This is very different from even and odd numbers, but there is a relation to that concept. Well, a function is called even if it's symmetric over the y-axis. Now you might say, well, what about the x-axis? Well, we'll get to that. And a function is called odd if it's symmetric over the origin. You might be like, what the heck are these terms for? Even is a borrowing because of what functions typically are even. So, for example, the function x squared, which looks like this, y equals x squared, looks roughly like that, or f of x equals x squared, and it is symmetrical on both sides. That's why we call it an even function, because the power is even. X to the fourth is another example of an even function. X to the sixth, x to the eighth is even. All these are even. Even x to the 0, in other words, 1 is even, which is kind of weird to think that 1 is even, but any number, any constant is even only if you're using even as a function. Of course, 1 is not even as a number. 1 is not an even number, but it is an even function. The function f of x equals 1 is an even function, as is the function f of x equals 2, and the function f of x equals 2.5. All of these are even functions because when I look at the power of x, it's actually to the power of 0. Power of 0 goes away, so this is really just 2.5. So we'll think of constant functions as being even functions. Remember, even functions, not even numbers. Algebraic check is if we're going with respect to the y-axis, you can rewind in the video and you can see what we're talking about. Symmetric over the y-axis, that means x has to switch to negative x, because we are flipping over that y-axis like this, and the x values are going to change while the y values are going to remain the same. So x goes to negative x, that's the algebraic check. And for odd functions, well, we're symmetric around the origin. X has to go to minus x, but y also has to go to minus y. So in other words, you're replacing x with negative x and y with negative y and seeing what you end up with. If you end up with the same function again, then it turns out that this is either even or odd, depending on which ones you replaced. I know that seemed abstract, so let's do this as an example. F of x equals x to the third minus x. Well, first things first, I'm going to look at the two pieces that make it up. See this power right there, x to the third, that's an odd power. And x, well, it doesn't have a power right here, but this power right here, that's x to the power 1. X to the power 3 and x to the power 1. They're being subtracted from each other, and any two odd functions that you put together are always going to be odd. So if you do odd plus or minus odd, you'll get another odd, which is interesting because that's different from how we see it with numbers, but that just goes to show that this is not the same thing as we do with numbers. Odd plus odd equals odd for functions. Odd plus odd equals odd for functions. So this is an odd function. Let's see how we can actually determine that. Let's say we didn't want to have to rely on our knowledge of the powers. Here's what we would do. I am going to remember that this is y. Let's change this up. So let's see if I want to figure out if it's even. I'm going to replace x with negative x. So I'll do negative x to the third minus negative x. And I want to see what that equals to. Well, to simplify, negative times negative times negative, that's negative to the third power. Negative 1 to the third power is going to be negative 1. So this will end up negative, and it'll be x to the third. This will be minus a negative, and so it will be plus. So we've got negative x cubed plus x. Now that is not the same as what we started with. Notice, as I erase here, what we started with is x to the third minus x. This is negative x to the third plus x, almost the opposite. Well, that leads me to believe if it's the opposite, then maybe if I replace y with negative y, we'll start to get something more. So it's not even because we didn't end up with the same function again, but if it is odd, then if I replace y with negative y, I should get something. Now I've already replaced x with negative x, so to do odd, I'm doing both. I'm taking the fact that I already replaced x with negative x for this part, already done my replacement there. Now I'm going to replace y with negative y. So this is negative x to the third plus x. And now to simplify this, I need to, of course, put y by itself without any negatives here. So what I'm going to do is divide both sides by negative 1. I'm dividing both sides of the equation by negative 1. Basically, I'm just changing the sign of everything. y, negative y will become positive y, or whatever y happens to be. It doesn't have to be positive, but it is not negated. And negative x to the third power, well, I'm dividing by negative 1. Negative 1. If I'm dividing by negative 1, then that better be positive x to the third. And this one, plus, will become minus. And notice that I ended up with the exact same function again. Exact same function again, as it was right here. F of x and y, of course, meaning the same thing as one another in this case. So y equals x to the third minus x is the same here. So in other words, here's what happened. When I replaced y with negative y and x with negative x, I ended up back with the exact same function. So doing two replacements, both x and y, making them negative, turned it back to the same function. And look at this. When I did just x to negative x, that didn't end up the same. But when I did x to negative x and y to negative y, then it ended up the same. So this function is odd. And so our answer to this would be, it's odd. Running out of space here. Sorry, this is really low on space. And they say describe the symmetry. Well, odd is symmetric with respect to the origin, so I guess we would include that it has origin symmetry. So I'll erase a little bit of this and say the symmetry is origin symmetry. So it's odd symmetry. In other words, it's origin symmetry. Those mean the same thing. Odd is just particularly for functions. Odd functions are ones that have origin symmetry. That's the idea. Odd functions are the ones with origin symmetry. It just so happens that this odd power helps us to figure that out. Okay. Now if I look at, I'm going to skip 8 for right. Well, no, let's not skip 8 for right now. Go look back at 8. X squared plus negative x squared plus 6. This is negative x squared plus 6. Well, I'm looking at this power of 2. That is an even number. And this is x to the 0 because there's nothing there. So 0 power, x to the 2, x to the 0. Both of those are even numbers. So this function is going to be even, which means it has y-axis symmetry for being even. Even, it has y-axis symmetry. To go through the long way to do that, because I want to show you it fully, I'm just going to replace x with negative x because that's my check for even. And if it's even, then I know it's not going to also be odd. So I can stop there. So I do y equals negative x squared plus 6. So I change x for negative x. And I notice that negative times negative, because this is a negative squared, is going to be back to positive. But I'll pull this negative down, and this negative will cancel itself out. So this is x squared plus, or sorry, negative x squared plus 6. So it's the same thing as we started with. So we ended up, when we replaced x with negative x and then simplified, it was the same exact function again. So it's the same thing. If we look at, now I'm going to breeze through these a little faster. I'll leave it as an exercise to you to figure out what this is right now from, is it even, odd? Well, I see an odd power. I see an even power. If I put the two together, well, I don't know what happens when I add the two together. So here, so far, we have rules that odd plus odd makes odd. Even plus even makes even for functions. Let's see what happens when we do odd, odd, and even. So in other words, these two together will make an odd function, the two ones on the end, because they're both odd. What about this? How does this affect it? So here's what we'll do. We will plug x in for negative x to see if it's even. Negative x in for x. Negative x to the third power minus negative x squared minus 2 times negative x. This results in negative x cubed minus x squared plus 2x, which is not the same as before. Not only is it not the same, it's not the negative either. It's not the exact opposite because this one has been negated. This one has remained the same because it was already negative and it's still negative. And this one seems to have been negated. So really, It hasn't obeyed anything across the board. These two got flipped. This one remained the same. Odd parts, even parts. Well, maybe if I put another negative in front of it. So negative y equals negative x cubed minus x squared plus 2x. Remember, at this point, we've decided it's not going to be even because it's not the same when I change x for negative x. And that's our test up here, x going to negative x. Well, if I change it to negative y, then really that's just the same as switching the opposite side. So I'm going to do y equals, divide both sides by negative 1, x to the third plus x squared minus 2x. And that is also not the same. Two of the terms are the same, x to the third and minus 2x. Both those terms are the same, but the x squared has changed sign. So this is neither. It is neither odd nor even, and that's very easy to remember, that odd and even, when added together, actually give neither. Odd and even when added together give neither. Or subtracted, added or subtracted. This one, there's really nothing we can do except plug and chug. So I suspect this might be even, but let's find out. We start off by checking even by doing x for negative x. Always check even first. Y equals square root negative x squared minus 4. Well, negative squared is going to cancel out, so this is really y equals square root of x squared minus 4, and look, this is the same as what we began with. So all I did was replace x with negative x. I didn't do y with negative y, so this is even. This is an even function. For this one, I can use my shortcut to see that this is odd because this is really negative 8x to the negative 1. X to the negative 1 is the same as divide by x, and negative 1 is an odd number. In other words, there's only an odd power of x in here. So this is going to be odd, but let's see that all the way through. So I don't want you to rely just on that. If it's going to be odd, it should be the same when I replace y with negative y and x with negative x. Now I could go and test the evenness first, but I'm just going to go straight up and go straight to testing odd because we already suspect very strongly that this one is odd. So I'm going to do negative y because I'm replacing y with negative y. Remember, that's the same thing as y. And I'm going to replace x with negative x. Negative 8 over negative x. Put that in parentheses. Negative divided by negative is positive. So this is y equals negative y equals 8 divided by x. Move the negative to the other side by dividing both sides by negative 1. So I'll divide by negative 1 on both sides here. And all that does is switch the signs of everything. Y equals negative 8 over x. Same thing as we began with. So this function is odd, because when I replaced y with negative y and x with negative x, I got back to where I began, negative 8 over x. Really, you're just looking for these sign changes. F of x equals absolute value of x plus 1. I have a feeling this is going to be neither, but let's see. We'll check for even. Well, if I do y equals negative x plus 1, absolute value, this is y equals the absolute value of 1 minus x, or negative x plus 1, doesn't really matter. And that is not the same as what we started with, so it ain't even. Well, if it's not even, maybe it's odd. Well, if I take y and replace it with negative y, replace y with negative y, and leave x replaced, because I'm going to leave x alone since I already worked on that, negative y equals negative x plus 1. There's an extra absolute value sign in there. Absolute value of negative x plus 1. Well, that's y equals negative absolute value of negative x plus 1. Lots of negatives in there. Make sure you keep track of that. Remember, from this step to this step, I'm just dividing by negative 1, putting an extra negative on the whole thing. Negatives can go through absolute values like this, so you could simplify this down to y equals x minus 1 absolute value. but clearly that is not the same as what we started with, so this one's neither. Neither. Oh, and I forgot to go back and describe the symmetry. Remember, anytime it's odd, it has origin symmetry. Whenever it is even, it's got y-axis symmetry. So we'll go back here, y-axis. Neither would have no symmetry. And odd would be origin symmetry. Remember that odd and even are really just different ways of saying origin symmetry and y-axis symmetry. What's great about all this is that you can now tell whether a function is odd or even basically just by looking at it most of the time and sometimes by plugging in different pieces. But what you have is that since you can tell if it's odd or even, you can really tell the symmetries. You can tell what the graph it looks like. You can tell the symmetries of that graph. Is it going to look the same across the y-axis? Is it going to look the same when I turn it 180 degrees? Just by looking at the equation. Because you can know if it's odd or even just by doing this work with the equation, and then you don't even need the graph to know, hey, it's going to be symmetrical. So we never looked at this graph of x cubed minus x, but we know it's got to be symmetrical when we turn it 180 degrees because it turns out to be an odd function. All right, hope this was helpful. I know it was too long. Give me some feedback on this because I know that the format, of course, is not good. I have a document camera at home, but I wanted to get this to you as soon as possible. But give me some feedback on it, and we shall go from there.